Okay. All right. There you go. Can you see my notebook?
Yeah.
Yeah, perfect. So here's what we have. Okay, so when you put an ionic compound in water, all right, it's going to dissociate into individual ions, and then we call this side the unmixed state, okay, or the undissolved state, and this side the mixed state or the dissolved state, right? And when it comes to the unmixed state, what types of interactions do you see in the unmixed state? What do you guys think on chat? What interactions do you see? What forces do you see in the unmixed state? Anybody?
Hydrogen bonds, dipole, and dispersion.
Okay, so that is between water molecules, right? So we have water on the other side as well. That is true. Okay, we have both. Those forces on both the unmixed side and the mixed side. But what about other forces? What else do you see apart from what you see? The intermolecular forces you have between water molecules. What else do we have there? Anything at all? Okay. All right. What kind of a compound is sodium chloride? Okay. Okay. Now we're getting somewhere. Thank you, Maggie. But I'm going to come to that. Okay. We have. So I'm talking about the ion. I'm talking about the unmixed state. But yes. But if you think about the mixed state, all right. So we said that all the cations are surrounded by the water molecules, and that is what is meant by aqueous here. And all the anions are surrounded by the water molecules, and that is what is meant by the aqueous in front of the anion over here. Okay, so what is happening here is we have ion dipole interactions, in the mixed state. All right, so I did not draw the water molecules. You know that here they're supposed to be water molecules. You can draw the rest. So these are the dipole moments of the water molecules. The dipole moments of the water molecules, which I haven't drawn. Anyway, so yes, we have ion dipole interactions in the mixed state. That is true. Ions interacting with water, ion dipole or ion water interactions, ion solvent interactions. This is what we have in the mixed state. What about the unmixed state? What do we have in the unmixed state? Do we have any other interactions that we haven't mentioned in the unmixed state? All right, sodium chloride. What kind of a compound is it? Sodium chloride is what kind of a compound is it?
Ionic.
Thank you. It's an ionic compound. Thank you. Okay, much better. All right. If it is an ionic compound, what holds the ions together in an ionic compound? What forces? What do we call these forces? Anybody? Thank you. Ionic forces, that are ionic bonds, that is it. All right. So we have ion-ion interactions, in other words, ion-ion interactions or ionic forces in the unmixed state. Okay. Now, is everybody clear on that? Are you guys, okay with what we have written on my notebook so far? Yes. Okay. Now the question is, let's take a look at this peg diagram. All right. Based on the peg diagram, the unmixed state has a lower potential energy than the mixed state. Yeah. So if we have the situation, where do we have stronger interactions? In the unmixed state or the mixed state? Go on chat. Thank you. Lower the potential energy, stronger the interactions. It's the other way around. Stronger the interactions, lower the potential energy, right? So since unmixed state has lower potential energy, you have stronger interactions here. Now, this tells me immediately what interactions are stronger, ion-ion interactions or the ion dipole interactions in the mixed state. What can you tell me about that? What interactions have to be stronger then? Thank you. The ion-ion interactions are stronger than the ion water or ion dipole interactions in the mixed state. Okay, so that is one of the things that we can immediately conclude from this peg diagram. All right, so let's take a look at this. Okay, it says interact more strongly with water molecules than themselves. This is wrong. Okay, here we are describing iron water or iron dipole interactions. They are weaker because mixed state has a higher potential energy. So that the first statement is wrong. Second statement, the free ions have more configurations than the ions in the crystalline network. All right. So where do we have the free ions? In the unmixed state or the mixed state? What do you think? Thank you. In the mixed state. All right. Because in the mixed state, ions are separated from each other. They're free from each other. Okay. So they have a higher number of configurations than in the unmixed state. Therefore, this statement is correct. The free ions have more configurations than the ions in the crystalline network, because you can see that the number of configurations in the mixed state is greater. Okay, so this statement is correct. Third statement, ions interact more strongly with themselves than water molecules. What can you tell me about the third statement? True or false? Thank you. It's true, right? Because that means iron-iron interactions. Iron interact more strongly with themselves means iron-iron interactions are stronger than the iron-water interactions. That's what we said here. Since the unmixed state has a lower potential energy, iron-iron interactions, that means iron interactions with themselves should be stronger than the iron interaction with water molecule. Therefore, the third statement is correct. Yes? Okay. Last statement, the free ions strongly constrain the movement of the water molecules. What can you tell me about that? Yes or no? Yeah, that is not true. Okay, if it is constraining the movement of the water molecules, you should have a lower number of configurations in the mixed state compared to the unmixed state. Since you have a higher number of configurations in the mixed state, the decrease of the number of configurations in the mixed state should be lower. Okay, that's what this says. So therefore, the fourth statement is incorrect. Therefore, the correct statements are there's the statement B and C. I'll call it B and C. Questions about that from anybody? Any questions, concerns, comments? Okay, so we just learned how to tackle a problem like that. All right, I just showed you the way I would think about it. Okay, if you have any questions, please let me know. Okay. All right. The other question I want to go over here is, let's see. I wonder if Grace is here now. Okay, so these two. Anyway, other question I want to go over here. Let me see. We talked about. You know what? Let's talk about this for a second. What would you pick? I'll say that this is A, B, C, and D. What do you guys think? Can you pick the right answer for this? All right. Here's a poll. I'm going to keep a tab on who's answering and who's not answering now. All right. Yeah. What do you guys think? A, B, C, or D? Go. On the poll now. Okay. All right, please submit your answers on the poll.
I don't have a poll on mine.
There should be one. Can you refresh your Zoom or something like that? I mean, maybe it will work. There should be a poll there on Zoom because I see the answers now. 80% answers. Keep me posted, okay? All right, I think that should be enough. Okay, so I already have more than 80% answers. So based on that, let's see. Now, the question is, which compounds are likely soluble in water? All right, to do this, we look at the charge product. So that's the last thing we talked about the other day. If the charge product, that means the charge of the positive ion times the charge of the negative ion, if this is greater than or equal to 4, what can you tell me? Is it soluble or insoluble?
Insoluble.
Thank you. If the charge product is greater than 4, it's going to be insoluble. In other words, if the charge product is less than 4, it's going to be soluble. If you think about the first compound over here, sulfur is -2. Therefore, copper has to be +2. Therefore, the charge product is 4. Let's think about the absolute value only. Here is 4. Therefore, copper sulfide, CuS, has to be insoluble. In aluminum phosphate, we are told that phosphate has a 3- charge. So this guy is -3. And then aluminum has to be +3 then. Therefore, the charge product has to be 3 times 3, 9. And that is greater than 4. Therefore, that is going to be insoluble as well. And in strontium sulfate, sulfate is -2. You are already told that. And then strontium has to be +2 then, because that's how we can achieve the charge neutrality. Therefore, the charge product is 4. Therefore, strontium sulfate, soluble or insoluble? What do you guys think? Option C, soluble or insoluble? Thank you. Insoluble. That's it. And the last compound, carbonate, is -2. You have already told that. And then potassium has to be +1 because 2 of potassium is +2. Therefore, 1 potassium has to be +1. Therefore, 1 times 2 is the charge product, which is 2, which is less than 4. Therefore, potassium carbonate is supposed to be soluble in water. There you go. Yeah, so the correct answer is potassium carbonate. Any question about this from anybody?
I have a question.
Yeah.
It has to be less than or equal to 4?
If the charge product is greater than or equal to 4, then it is insoluble. If it is 4, it is insoluble.
Oh, okay. Thank you.
Yeah. So it has to be less than 4 if it has to be soluble in water. This works 93% of the time. All right. So with that, what I'm going to do is I'm going to end the poll. Okay. Let me see. I want to do one of the, here's the one. Okay. Let's do this question. This is going to be hard. Okay. Anyway, to do this problem, they're asking about the melting temperature. They want you to arrange them from lowest to highest. Okay. So now to do this, what we're going to look for is charge product and the distance between the ions. That is it. Okay. Because remember the ionic force, if you can see my notes here, ionic force is directly proportional to the charge product and inverse proportional to the distance between the ions squared. That's what we learned. And when it comes to calcium oxide, potassium oxide, sodium oxide, and strontium oxide. So the first thing I'm going to do is I will write the charge products here. Okay. So calcium is +2, oxygen is -2, potassium is +1, oxygen is -2. This is sodium. Sodium is +1, oxygen is -2. Strontium is +2 and oxygen is -2. Therefore, the charge product for these guys are, this is 4, this is 2, this is 2, and this is 4. Therefore, we know that this compounds has to have a higher melting temperature than the compounds in the middle, because the first thing is to look at the charge product. Since the charge product is greater in calcium oxide and strontium oxide, they need to have a higher melting temperature because the force is stronger there. And now between calcium oxide and strontium oxide, let's write them. So let me write here. Strontium oxide and calcium oxide. Which compound do you expect to have a higher melting temperature? Strontium oxide or calcium oxide? What do you guys think on chat? Which one should have a higher melting temperature? Thank you. Yeah, the one with the smaller distance between the ions. Yeah, there are no bonds here. I mean, there are no covalent bonds per se. So it's about the distance between the ions. Calcium and strontium are on the same group. All right. So here's my oxygen, anion. Okay, -2. That's a -2. Okay, and strontium is a much larger ion compared to calcium. Okay, you have a smaller distance between the ions here with calcium oxide compared to strontium oxide. Therefore, you're going to have a stronger force in calcium oxide compared to strontium oxide. So melting temperature will be higher here. And the same thing goes with sodium oxide and potassium oxide. Sodium is smaller than potassium K2O, because they are in the same group. Oxygen is again the same thing, -2, and here's the -2. They are the same size, okay? But potassium is larger than sodium, because they are in the same group. Okay, sodium is in a higher row. And as a result of that, you're going to have a stronger force in Na2, sodium oxide compared to potassium oxide. So therefore, this should be 1, this should be 2, 3, and 4. All right. Questions, concerns, comments. How can you tell the size of these ions? Sodium and potassium, for an example, Serenity, are in the same group. Do you see my notebook? Not the notebook, the textbook page. Yeah, sodium and potassium are in the same group. Potassium is below sodium. That means potassium has to be a larger ion compared to sodium, because you have more shells in potassium. That means that's going to make potassium larger than the sodium. Yeah, Serenity, did that help? Okay. So when you go down the group, what is going to happen to the size? Everybody, when you go down the group, what is going to happen to the size of the atom? Thank you. It gets bigger. Okay. The reason is you are adding more shells. That means the atom is going to get larger. So since potassium is below sodium, potassium has to be a bigger ion compared to sodium plus ion. Yeah, that's it. And the same thing with calcium and strontium. Calcium and strontium are in the same group, but strontium is below calcium. Therefore, strontium has to be larger than calcium. Yeah.